Boom. So there's the recording. So welcome everybody. Let me get a few more of our classmates in there. How do I do that? Admit.
Yeah, I definitely noticed a difference after oiling this thing because it was like stiff and was really hard to move the action on it. After oiling it just glides.
Right. Yep.
And it's nice because it has the highest tooth count of any ratchet ever made at 162.
Yeah, the fine tooth ratchets really benefit a lot from lubricating them. But you can say that with just about anything, like our engines, our transmissions, right? The key to having stuff last a long time is that lubrication. So likewise, there's lube in our superchargers and turbochargers. So with that, let's jump into this thing. So I will put it on slideshow mode and we'll get going. So forced induction, man, you know, it's super popular. We've seen movies. It's actually been around a long time.
Hey, Professor, did the book half book ever get sent out or no?
You know what, Frank? I need your address. I did send some out, but I still have a whole stack of them here. So, and I don't know how I screwed up and didn't get your address, or I might have deleted it, or.
Can I just pick it up later?
Because I know
I'm going to do another run, and I want to get those books out to you. So, if
can I just stop by and pick it up?
Sure, you could do that. So we'll set that up because I got books for you.
I know you plan on bringing the pit bike to me. Would you be able to bring the packet then?
Okay, yeah, we can do that. We can do that. I should be able to get into the college next week on like Thursday.
Okay.
The college allows us to enter it on Mondays and Thursdays. So.
Yeah, I know I have more than just the pit bike there. So would you be able to?
Can you send me a list of all the? Send me a list of all the stuff.
Okay.
Oh God.
That actually.
Can of words.
Yeah, I know it's getting. But like if you said, I know you had the pit bike and a carburetor and maybe like a helmet or something. And
yeah, I just was looking at the pit bike, the carburetor, the helmet, and the gas tank there.
Yeah. Okay. Well, we can do it.
Well, if you want to coordinate, maybe I could pick up Nathan or some on Thursday. If you're going in there and you got limited time, maybe we can just throw it in the back of my truck. Just stay in touch.
Yeah. So I was thinking about grabbing your bike, Nathan. I had to be out of there by 2:00, and I was helping Eric with some transmission donations, and we were running short on time, so we barely got out of there before 2. The police were chasing us out, and it's kind of funny because they wanted us out of there and we couldn't get out because they had ripped apart the sidewalk, and I ended up having to drive a pickup truck up on the curb and like cut through actual campus to get to the parking lot by the parking garage to get out. So anyways, it's a little crazy. The really isn't set up.
If Frank is able to help, that'd be nice.
Yeah, I got time.
We will.
I might have to leave a little bit early. I got a something to look at, but I'm waiting for them to call. But
good. Okay.
I'll watch it online.
We'll coordinate that next week then. All right. So back to forced induction. Been around a long time. 1800s, back when they were doing a lot of gold mining and mine shafts and coal work, right? They would use big pumps to pump air down into the mine shafts. And so that's, if we look at our very early routes to, where superchargers and stuff come from, that's where they come from. Most of the ones that we hot rodders think of, like you saw on the Ford Falcon of Mad Max and stuff, they were early blowers adapted from 2-stroke diesel engines. And so we can't talk about superchargers without talking about this guy right here. And what's cool about it, and of course what's phony about it. So let's see if my my link works here. And I will share my screen.
If you start critiquing Mad Max, I will kind of go insane.
Oh, I love Mad Max. But I want everybody to watch this part right here.
It's one of my favorites.
Okay, so he flips the switch. Did you guys see that? All right. So one thing about Mad Max is it makes you think that with the flip of a switch, you can turn on your supercharger.
Perfect.
And with the flip of a switch, you can turn it off. And that's not really how that works. I mean, it's a cool concept, but if you want something with extra power at the touch of a button, really what you're after is nitrous there. So let me switch this back to our presentation. And so these superchargers that we commonly see were actually in the 30s and 40s and 50s. The diesel engine that was really popular in like dump trucks and semis and stuff was a 2-stroke diesel engine. And to make that thing work properly, they utilized a supercharger or a compressor to pump air through the engine. So check this out.
The position of the piston is just as crucial in this 2-stroke diesel engine. Its exhaust valve must open and close at the right point in the engine cycle. In one 2-stroke engine cycle, the crankshaft makes 1 revolution. How does this compare with a 4-stroke engine cycle? How many revolutions does its crankshaft complete?
All right, so let me back up because I let it play too far here.
The position of the piston is just as crucial.
All right, so what you're looking at is an animation from CDX about a 2-stroke diesel engine. And, you know, for years and years until we came up with advanced turbochargers and stuff in the 80s and 90s, moving on to today, you know, if you wanted a powerful diesel, 2-stroke diesel was one of the most popular options. So if you look at the way these old diesels were set up, they still had an exhaust valve. I guess I should have made that red. They still had an exhaust valve here controlling the hot exhaust gases flowing out the exhaust manifold and stuff. And so you would still have a camshaft for that. But on the intake side, they just had intake ports on the sides of the cylinders. So the fresh air fuel mixture would come in the cylinder sides. And so like a 2-stroke, you know, one revolution of the crankshaft is all it took for a complete cycle. So even though the engine was turning less RPM, it was getting more power cycles per minute, and that increased its efficiency. But we had to have a way to get the air to enter the engine and then be compressed. And so they put this big supercharger on here, or Roots blower, to basically pump air into the engine. So whenever the piston moved down and it uncovered the intake ports, the charger would then blow air inside the engine. It would move up. The fuel injector would squirt the fuel in as the piston was nearing top dead center, ignite the fuel, burn it, and the exhaust valve would open up, and then the air pump would then help blow those exhaust gases out as it blew fresh air into the engine. So in the 40s and 50s, they were, you know, putting these superchargers on these 2-stroke diesels, which came in different sizes. Some were 6 cylinders, some were, they later evolved to V8s and stuff. Well, it wasn't before not too much longer that the hot rodders of the day adapted that design to an engine, and they would put these blowers that were on the side of this. Here it's inline six engine, 2-stroke diesel. They adapted it and used them on their hot rods and stuff. So they were supercharged in everything from flathead Fords to later small block and big block Chevrolets. So it's kind of neat to look at the history of this. So remember, with forced induction, right? We're increasing the amount of volume of air fuel mixture that can go through the engine, right? We've been talking about how there's a common saying that there's no replacement for displacement, and the engine's essentially a pump, and the more you pump through it, the more power it can make. And so you're limited by how big that engine is. Well, once you use forced induction, now we can increase that volume, and essentially it's almost like having a bigger engine in the same space, right? Because we're increasing the displacement of that. And that displacement is going to be related to the speed or rotation of the supercharger. So in this equation, we are dramatically improving the engine's volumetric efficiency, where it might have been 80 to 85%, maybe 90% if it's an efficient overhead cam type vehicle. Well, now we can go way over 100% volumetric efficiency in the engine's operation. And by doing so, we can make substantially more power. All right, so the first one that we're going to focus on, since we were looking at the history, is we're going to look at superchargers, because those have been around the longest. And they're all driven off the engine by some mechanical means, typically a belt. Now, of those superchargers, there's 3 different styles. There's the screw style, the centrifugal style, and the root style. So 3 different styles there of superchargers. The root style is arguably the most common, and it's been around a long time, patented by the Roots brothers, right? This style of pump, if you will, was what they used to pump air into the mine shafts in the 1800s. And it's used all over the place, even in OE production stuff. So our last year of the old Mustang, the Mustang Cobra from 2003-4, that used this root style blower. Your Buicks that came with, like, your Park Avenues and stuff that came with the supercharger on there. This root style blower is a very popular model. It's a positive displacement, meaning that every time this thing rotates, it's going to pump X amount of air, right? Kind of like your engine has a certain amount of displacement, right? Let's say you have a 350 cubic inch engine. Well, that means that every 4-stroke cycle, every couple revolutions, it should move 350 cubic inches of air through it. Well, this is the same deal. Every revolution of this blower is going to pump a certain fixed volume of air through it. Okay. So this style of supercharger gives you external compression, and that the compression takes place outside the blower. So it grabs the air, it forces it through it, and then compresses it on the exit. And it really is just that. It's acting as an air pump, right? So this root style blower, this is what was used on those 2-stroke diesels. It's the one where you see it's got 3 lobes on there, right? And with it, you maintain a pretty consistent boost pressure across a wide RPM range.
If it is technically like an air pump, doesn't that mean it could be electrically driven, meaning Mad Max wouldn't be too far-fetched?
Yeah, except in Mad Max, they had it driven off of a belt. And the thing is...
Oh, yeah, that is true.
Yeah, the thing is that all the airflow has to go through it, right? So
yeah, because I know there are some blower systems for stuff like in like industrial, like gas masks. They'll have blowers to provide extra air coming through because it can get pretty restricting. And I know those are electrically driven.
Trying to see if I got a better picture, but I guess this is a pretty good picture, and I can draw on this and make this better. So if we think about the Mad Max car, right, here's the roots blower, and you can see the rotors have been pulled out, right? But imagine here's my, you know, big Holley carburetor double pumper, and he's bolted. I guess I kind of drew him off center, but he's bolted to the top of this thing, right? So if this is my carb, what that means is that all the airflow going through the carburetor has to then go through the blower, which it has to pass. I move this back to the drawing tool. The air has to go through the carburetor, and then it's got to go through the blower, so it's got to pass in between these rotors. Well, these rotors are pretty restrictive for airflow unless they're rotating, right? Because when they rotate, the air can fill up this pocket here. It can go through and be compressed and forced out. But if this blower is not rotating, it's going to stall out the airflow. So remember that the engine is below the blower, right? He's sitting right on top of the intake manifold. So the pistons, and I'm doing a terrible job drawing this out, but, and here's my intake manifold ports and stuff. They can't get the air from the carburetor to the, you know, to the cylinders because this guy's a big restriction. So what makes Mad Max phony is that he's turning this thing on and off. And you could set up like a AC compressor clutch and engage it and disengage it so the compressor turns and then it doesn't turn. And if you search around, there's guys that have built their own Mad Max Ford Falcon, and they can have it engage and disengage. But to get the car to run, they actually had to take out these rotors. They had to take those rotors out of there so that the thing would run when the supercharger was turned off, right? So that's why Mad Max is phony. Like the supercharger always, this style of blower always has to be spinning, otherwise you couldn't get air to the motor, right?
I think another thing that is weird about Mad Max is that their Falcon was placed on a Ford Ranger body.
Yeah, so in Australia they have different models. Whatever. They have different models of cars than we have, and so that was the Ford Falcon was a pretty popular car back then for Ford, and it just wasn't a model that we got in the United States, unfortunately. I think.
Yeah, only Australia got it, I think.
Yeah, they thought that would compete with the Mustang and other things. So pretty neat car, and it's a lot of fun if you go back and you watch the V8 supercars, and there's some improved production racing that they still do where they'll run those types of cars against other things, including RX-7s and all kinds of stuff. So there is some great racing to watch that comes out of Australia. They are real motorheads. But anyways, so this root style blower typically have 3 lobes, 120 degrees apart, so you can see the lobes, and of course the other one's facing down. What they've done is they've angled these lobes now. It reduces the noise. It improves the overall efficiency, having them on this helix. So that's something that's come about in the last few years. Essentially, the fuel going through here from the carburetor, that fuel kind of lubricates this thing. But they will also put some newer ones. They'll put some Teflon on the tips of the roller vanes there to reduce friction. Is there oil in these things? Yes, you can't see it in this particular slide, but in the front cover, there's going to be a set of gears that spin these dudes. And so the front gear set at the front of the blower has a small amount of oil that stays in the blower. So it's not lubricating. It's not lubricating these, but the gears in the front do get lubricated with a little bit of oil inside there. Obviously, with this style of blower, keeping the intake track clean, like running an air filter and not letting it suck a bunch of dirt in here, is important because it keeps the rotors from eating up a bunch of stuff and getting worn out. Eventually, though, that's what happens. You lose compressor efficiency as the rotors themselves wear. All right, let's clear those drawings, and we'll keep going. Here's a better shot of the gear set at the front, where you can see that would have a little bit of lubrication in there. This one's driven off of the serpentine style belt. One thing about a supercharger is it takes a certain amount of horsepower from the engine, right? So we're going to take horsepower from the engine to run this pump. So it does take power to make this thing go, but if the engine's turning, guess what? These guys are turning. And so this style of supercharger, because it's positive displacement, it does make great low-end power, right? It really improves the power, the torque, even at low speeds, because you're pumping it in there with the engine RPM. So, all right, clear that, and we'll move this back. All right. So the end plates support the rotors. We talked about the front and how we're going to have a gear train there that we want to lubricate, and of course that maintains rotor timing or rotor phase. That's important. A lot of times that oil is like a lifetime fill, but it definitely wouldn't hurt to change that oil out of there every 60,000 miles or so. Now we have to have some method to protect this assembly in case of a backfire, right? And all you guys that have been through the engine class that had your timing off a little bit, you know, it's backfires can happen. If the air fuel mixture goes too lean, it could backfire. If you're firing the spark plugs at the wrong time, it could backfire, right? Well, we don't want it to backfire.
What if it's just like a D-cell pop? What about that?
Well, anything like that could damage these rotors, right? So we have to have an exit strategy so that if there's any backfires that's forcing air, fuel, and some fire up, that it doesn't shock these rotors and damage them. So how do we deal with that? Well, we got to have some type of backfire plate or backfire valve. And those are commonly a spring-loaded type of pop-off valve. So there'll be a specified pressure that this valve is going to pop off its seat, and it's going to release excess pressure. So that's usually from a backfire, although under extreme boost, it could start lifting up. So let's look at how that is going to work. If you had one of those classic root style blowers that you rigged off of a diesel, you know, you would have to have a lower intake manifold to accept it. And here's a good example of that lower intake manifold. And what you're looking at here right on the front is this blow off valve or plate here, so that if we get a backfire that comes back up, it's just going to lift this plate off its seat against that spring tension. And the spring tension controls essentially how much pressure it takes to make the plate come off of there. So that's the protection device or anti-backfire valve on one of these kind of old school blowers there. You have to provide some type of means, otherwise you would shock the rotors and damage the supercharger. All right. Now there's other styles of superchargers. Remember, there was three. So we did the root style blower first. Okay. The second style that externally looks very similar, often called a Whipple blower. It's a screw style supercharger. So this style supercharger has internal compression. The air gets compressed as it moves through. Actually, this one's coming this way as it moves through.
Currently, I believe
the
this one would be the king.
So it's a little different way to do it. Gives you a little bit more efficiency. Yeah. So here's a good animation of how these rotors inside this are a screw thread, and again, the faster they spin, the more boost pressure they create. It's a little bit more efficient, and it makes more. It's a little bit more efficient. It creates less heat in the air as you pressurize it. And so I have here, hey, this works pretty good for like a tow vehicle or something where you're not trying to get a massive amount of boost. So they are limited in how much boost you can make, because all the boost is basically made as the air moves through those screw style rotors. But it's a more efficient style supercharger. So we have seen on some vehicles that they use this style supercharger on their Mazda used it on their Miller cycle engine. It is a more efficient way to go, but it is limited in how much boost you can get out of that. So usually it's a lower 5 to maybe 15 psi maximum boost level with this style of supercharger. All right. So that leads us to the third style of supercharger. And really, when it comes to performance, the root style is really popular because it gives you boost right away. But if I want a whole heck of a lot of boost, if I want maximum air, intake manifold pressure, that's where this style of supercharger really comes into its own. The centrifugal style, it essentially looks like a turbo hanging off the front, but what makes it a supercharger is that, remember that this unit is still mechanically driven, so we can see a shaft through here, and it would run down to a belt. And so as the engine turns, it turns this shaft, which turns the supercharger. So the compressor side of this thing is very similar to the compressor side of a turbocharger. However, it's driven off the engine, so technically it's a supercharger. All right, centrally mounted impeller to compress the air. Clear that stuff out. We'll keep this going. So with this guy, you don't just have a fixed volume, right? The faster you spin the impeller, the more boost you get. So it makes maximum boost here, maximum boost at maximum engine RPM. And likewise, you have less boost at low RPM. So the nice thing about this design is for maximum power, if you're trying to make the absolute maximum horsepower, this unit will do that. In a lot of cases, it's easier to put together packaging wise on the engine because you're not trying to drive it off the exhaust gases like a turbocharger. So you don't have all the exhaust plumbing complexities. Go ahead.
Wouldn't it be debatable that would be make the max power when you can twin charge the vehicle with a screw supercharger to have the low boost with that and then higher boost with the turbo?
Are you talking about like progressive turbos? Yeah, it's
No,
still
like
it
actually
gets
putting on both a supercharger and a turbo and twin charging the vehicle, because I know that you can do that as well.
If you start doing a lot of that, it gets pretty complicated, like packaging wise. Just on average, if your goal was to make a whole lot of power, you can make a lot of power with this design. But where you're not going to get a lot of power is at the low engine RPM side of the equation. Okay, it acts very much like a turbocharger in there, in that it takes a while to build up that boost pressure. So I have on here, this design is popular if you have traction limited or application where large amounts of low end torque is not needed or desired, right? So if you're already lighting the tires coming off the line, you know, this design might be good. If you're doing like a Bonneville type car that's high RPM power, where you want to make maximum horsepower at higher RPMs, this would be a good choice for you, and you wouldn't have the complexity of routing the exhaust gases through a turbocharger. And that's kind of the advantage of this over a turbo, is that you're not having to mess around with the exhaust side of the equation, right? So we have to have a gear set in the front of this thing that usually is going to multiply the engine speed somewhere around 4.5 to 5 to 1 to get this thing to spin fast enough to work properly. So again, there's going to be some oil stored in a reservoir there to do that. See if I can. So if we look at these different pictures here, you can see, you know, here's the gear set over here. This would have oil in it. There's even an oil fill plug right there. So, and it's like 1/2 of a turbocharger, right? It just has the compressor wheel. So it does make packaging arguably a little bit better. It is still driven off the engine. So I still have to say that it does take some horsepower from the engine to run this style of supercharger, like all superchargers. But it can make a lot of boost pressure. And it, you know, tends to increase its boost and increase its efficiency at higher RPMs. So it's kind of like, well, where do you want your power? Do you want it now or later? And then how much do you want? So, all right, so that's the centrifugal style supercharger.
Once again, with twin charging, though, you would get the best of both worlds, because you can get the low end and the high end.
Yeah, it gets pretty complicated though. I mean, like, it's not super
Yeah,
practical.
I've seen some setups, and you'd be like, yeah, that would seem like it'd be a lot.
Yeah. So because these are all driven off the engine, typically again through a belt, one of the things that we get to do with this is we can control the boost by controlling the speed of the supercharger, right? And there's some variables there that come into play then, because it depends on how big the supercharger is and what's the engine displacement, right? What the clearances are inside the supercharger. What's going on with your valve timing and your camshaft will affect essentially your effective compression ratio. A big thing about these is trying to prevent belt slippage. At high boost levels, you always tend to get some belt slippage from that. And then ultimately, you do have to have a nice free-flowing exhaust because you're pumping so much more air in the engine, right? So what's the ratio between these two pulleys? What's the engine displacement? All that stuff. There's some calculations for us to figure out so that we can estimate what our boost ratio is going to be. So with that, if you know, we could have an underdrive, which means that the supercharger is driving slower than the engine. It could be a 1-to-1, or if we want a lot of boost, we could have an overdrive where we have the supercharger is actually spinning faster than the engine, right? And so usually you change a tooth on one of those pulleys, you're going to get about a 3% difference. So you're either going to increase boost, right, with an overdrive, but that's going to decrease the belt life, decrease the supercharger life, maybe blow up your engine, but you're going to get more power. Or if you decrease if you go to an underdrive, it's going to have the opposite. You're going to make less boost, have less power, but you're going to have a little bit more longevity of everything. Okay. Jonathan in there. All right. So let me clear those scribbles and we'll keep going. So underdrive, overdrive. And there's charts that, these charts are usually if you buy a supercharger that's part of a kit, they'll come in the instructions. You can get them online for different blower displacements, right? Because it depends, is it a 671, an 871, or, you know, so what is the displacement of the supercharger? What's the displacement of the engine? Here you can see we're looking at pulley counts on here to figure out what the drive ratio is going to be. Here's another one that probably is a little bit easier to see. So if you have this Gilmer style belt, which a Gilmer belt is the belts that have these ribs going across there. So I have that tooth style or Gilmer style timing belt there. And this one happens to have 3-inch pulleys, it looks like. Depending on the size of the engine, right? Because then it's like a bigger engine, it's going to take more volume of air to fill the engine, right? And then you have your drive ratio. So here's your 1-to-1, okay? Here's your overdrive. Here's your underdrive over here. And it shows you that, let's say I had this 350 here, and I had a 671 blower at a 1-to-1, it would give me 15.3 PSI in the engine essentially. So I can vary how much boost pressure I'm going to get by what do I do with these ratios. If I want more boost, I'm going to overdrive the supercharger and spin it faster. As you tend to do that, again, you usually end up with belt slippage issues. So it's definitely a compromise on what you're trying to do with the engine and how strong is everything built, right? Like if I'm going to be adding a bunch of boost, I better have pistons that can handle that, connecting rods that can handle that, a low end that's put together well. So there's a lot dependent upon that. If I go with too much boost, not only can just the cylinder pressures alone damage things, but I also really have to be worried about detonation, right? So the compression ratio of the engine and the gasoline type, because I'm trying to control my effective compression ratio. And I really got to be below an effective compression ratio of about 12.5 if I'm going to run pump gas, right? So one of your major limiting factors is detonation and what fuel you're running in the engine. So usually what happens is we want a lower static compression ratio as we're adding boost, right? So if I clear these out of here again, and I move this on, we can use this formula here to determine the effective compression ratio. You take the boost, you add 1 to it, divide it by 14.7, and that basically, and then you multiply that by your static compression, it gives you your effective compression ratio. So I have here, we have a 9-to-1 engine, 9-to-1 compression ratio engine. We're running 10 pounds of boost. Essentially, we're going to end up with a effective compression ratio of 15.1 to 1. So again, even though that engine only started out with a 9-to-1 compression ratio with 10 pounds of boost, I mean, that's a pretty high effective compression ratio. And that means that that engine's not going to be able to run pump gas. We're going to have to run, you know, race fuel or go to ethanol or something, because we're going to have detonation problems with that setup. So there's lots of stuff to take into effect. Here's another chart here. where I can't remember what, I think this is still the 671, but it looks at static compression ratios versus the boost, and then what your effective compression ratio would be. So it's basically doing this formula for us. And you can see that, again, if you're at a static compression ratio of 91, you add 10 pounds of boost on that, now you're up to 15 to 1. And remember, we want to stay, testing tells us that, you know, we usually want to stay below about 12 and a half. So really what we would want, if we were going to run pump gas, is we would want to stay around 8 PSI. Draw on this now. We were going to run 91 octane, we would have to be down at 8, an 8 to 1 compression ratio at 8 pounds of boost should give us the ability to run 91 octane pump gas. When we go beyond that, we're typically going to run into detonation problems. All right. So other things that to come into play, right? Ignition timing. We are going to back off the ignition timing as we add boost. And what you find is that as you're blowing the air fuel mixture into the engine through the supercharger, it creates a whole lot of turbulence in the engine. I didn't spell that right. T-U-R. And of course that speeds up combustion. So you can get away without the ignition timing because the combustion is going to physically happen faster due to the effect of the supercharger. So as boost comes on, ignition timing is you're gonna want to back that off. Coolant temperature, coolant temperature is a big deal. If I can run the engine cooler, right, I should be able to get more boost here because I could absorb some of that heat a little bit better. Obviously, intake air temperatures, I want to try to keep those low. With my spark plug heat range, I'm going to want to go to a colder spark plug because I'm making more heat for combustion, so I don't need that spark plug to retain as much heat. Combustion chamber design not only needs to flow well, but I'm usually going to want a lower compression value. And again, because I'm forcing so much more air into the engine, if I don't upgrade the exhaust system, well, then I'm going to end up with exhaust back pressure problems, and then that's going to be my stumbling block that limits the performance of my engine. So again, as always, one thing affects something else, all the way down the chain. All right. So that brings us to turbochargers. And so here we're looking at, it kind of looks like an LS engine here by the way the coils are set up on the manifold or on the valve covers and the way the intake manifold looks. It's twin turbocharged, right? And the one thing I want you to take away is when you go to turbocharging, man, there's a hell of a lot of plumbing that has to happen. Because not only do you have to have all the intake plumbing, right? So we have air that's going in, oops, see if we can get that going. We have air that's going in to the turbochargers here, and then it's going to be pushed out of the turbochargers, and maybe that's going to go down to an intercooler or something, and then ultimately it's going to go into the engine. So I have all this plumbing here, but I also have exhaust plumbing that has to be directed into and out of the exhaust side of the turbochargers. So turbocharging, it does make the engine more efficient because we're with our superchargers, we were taking horsepower from the engine to make more power, right? Well, here we're taking exhaust gases that normally wouldn't be giving me any extra horsepower, right? They just be flowing out of the engine, and we're using those to drive these turbos to make the engine more efficient. So with the turbocharger, your efficiency is up. It does become a plumbing nightmare though, as you can tell. And this is packaged well, it looks awesome, but think about getting that in the vehicle. I mean, that's a lot of plumbing and stuff that you have to fit underneath the hood of the vehicle. All right, so let's check out this video clip.
One way to improve engine output is to increase the amount of air-fuel mixture that is burned in the cylinder. That means increased volumetric efficiency, or how much air-fuel mixture is delivered to the engine. This is done by what is called forced induction. Forced induction increases air pressure in the intake manifold above atmospheric pressure. An engine using forced induction can have a volumetric efficiency of above 100%. One way to achieve forced induction is by using a turbocharger. It uses energy that's normally wasted through the exhaust. Exhaust gases enter a turbine and make it spin. The more gases, the faster it spins. A shaft connects the turbine to an intake compressor. It compresses the air and forces it under pressure into the intake manifold. The turbine operates at very high temperatures, and with the compressor can rotate it well over 100,000 revolutions per minute. So they both need a good supply of clean oil to lubricate their bearings and carry heat away. Some engines also supply coolant to the turbocharger body to improve cooling. On gasoline engines, higher and higher engine speeds mean more and more exhaust gases, and that makes the turbocharger force more and more air into the cylinders. This can damage the engine. To control this, a device called a waste gate is fitted to the exhaust inlet of the turbocharger. When air pressure in the intake manifold reaches a preset level, it automatically directs exhaust gases away from the turbocharger. The waste gate can also be computer controlled to reduce intake air pressure in the event of detonation or knocking. An emergency relief valve may also be fitted so that if the waste gate should fail, it can prevent an abnormal rise in manifold pressure. Since the turbocharger uses the energy of the exhaust gases, there is a short delay between when a driver opens the throttle and when maximum power is available. This is turbo lag. And on larger engines, it's quite noticeable. Because a turbocharger recycles heat energy that would otherwise be lost to an engine, can seem to be offering additional energy for nothing. The turbocharger can introduce problems of its own. Extra heat and power it generates can put an extra load on the engine's cooling and lubrication system. As the air passes through the turbocharger, it heats up. But hot air is less dense than cool air, so it tries to expand again, and some of the benefits of compressing it are lost. To stop this and improve efficiency, some engines use an intercooler to cool the compressed air. Fits between the turbocharger and the engine, usually air-cooled.
All right, so that had a lot of good information and a good overview on turbochargers. Everything it said about improving volumetric efficiency, well, that's the same as with a supercharger, but here we're improving the efficiency as well because we're using the exhaust gases, right? So like you saw in the video clip, the exhaust gas is driving this thing, right? And so the more exhaust gas flow you have, then the more intake air can be compressed going into the engine. So it does not require a direct mechanical connection from the engine to the turbocharger, but it does require exhaust gases to flow through there. So we end up with an exhaust side, the turbine wheel or hot wheel, and it's attached by a shaft to the compressor wheel or cold wheel. So this shaft is connecting one side to the other. That guy's going to spin at a whole lot of RPM, so it's got to be precisionally balanced, and everything else, and it's got to be lubricated well and oftentimes is cooled well by running coolant through the housing. So here's another shot where you can see we've taken off both the intake housing and the exhaust housing of a turbocharger, so you can again see the turbine side, right, and then you can see the compressor side of the turbocharger and how both those things are plumbed together. And we're going to have an oil feed line and a return, and oftentimes we're also going to be pumping coolant to the housing to keep this thing cool. You know, turbos are a heat machine, and of course, as they get hotter and hotter, they make more boost pressure and the engine makes more power until the point stuff starts melting down. So, you know, again, plumbing wise, turbochargers can be a nightmare. Heat wise, they're also pretty challenging as far as packaging that underneath the hood of the car and you know, managing all that heat that is created through the turbocharger system. So exhaust side is the turbine, intake side is the compressor. And of course, the angle of the fins here and all that has a great amount to do with how this turbocharger is gonna perform in the engine. Also, I guess I'll go back to this picture. The bearings inside here are important. So if I look at, you know, what are we using for a bearing? Do we just have a bushing in there and it's floating on oil? Or do we actually have ball bearings supporting this? It's a ball bearing turbo. That's going to allow this to spin a little bit easier. That also increases the complexity of the turbocharger, right? The faster and easier I can get this thing to spin up, the less turbo lag I'm going to have. And so the less delay I'll have between where I start making boost and where I'm not making boost, right? The big downside with the turbocharger versus a supercharger is just what the little video clip alluded to, is that traditional turbo lag or the delay time that you experience between when you start making boost and you start making additional power in the engine, right? You romp on it, and it's almost like a rubber band, like you start stretching out the rubber band and then it finally gives you tension and you launch and pull away, right? So, you know, it is definitely, a turbocharger is really, really dependent on exhaust gas flow, right? So if I don't have a high amount of exhaust gas flow, I'm not going to start the turbo spinning and I'm not going to get any boost pressure, right? The more exhaust flow, the faster I'm going to spin the turbo. How fast? Well, we can get speeds over 100,000. That's not a typo, 100,000 RPM. So again, good oil flow to the turbo shaft is really, really important. So as this thing starts spinning up at all this RPM, that's where we get the compressor wheel drawing in fresh air, compressing it, and throwing it out to the engine, right?
And that speed is also a reason why you shouldn't just shut off your engine if you have a turbocharged vehicle. You should let it sit idle for a bit.
All right. So Nathan, what you're getting to is, I guess you should punch up the chat here too.
Because if you just shut it off, it's not getting oil, but it's still spinning.
Yeah. So hang on a second here. We'll come back to this, I promise. But
there's a lot of slides.
So my turbo controls here, and that is, Nathan, what you're talking about, commonly people will have turbo timers installed in their engines. What a turbo timer is you can set how much time and how many seconds that this engine will continue to run after you shut the key off. And the idea is, I'm just going to exit out so I can go back here. Okay, so the idea is that if I, hang on one second here, I gotta get a, okay, get us back to where we were. You saw the little turbo timer control box. Now,
that's actually
I'm gonna get
great, because I didn't know those existed.
Oh,
I
yeah.
just
So
knew not to shut it off immediately.
Yeah, so if you read let's say you buy a turbocharged car and you get the owner's manual and you read through it, the owner's manual would say, hey, if you've been doing some spirited driving, don't shut off the car right away, like Nathan just mentioned, right? It would say, hey, let the car idle for a minimum of 30 seconds or 45 seconds or something. They would tell you to let it idle, sit there and idle a certain amount of time before you shut it off. Why is that? Well, that's because remember, we're pumping oil. We're pumping oil here, inside here, to lubricate the turbo shaft. Even if it's ball bearing or not, we're pumping oil in there to lubricate the turbo shaft. Well, if this turbocharger is smoking hot because we've been driving the snot out of this thing, there's a tremendous amount of heat on this exhaust side, and of course that heat radiates through here. If I shut off the engine quickly, I stop the supply of oil, and that heat will basically cook the oil and dry it out and cause it to sludge up and seize the turbo shaft. So why are you not just supposed to shut it off really suddenly? Basically, you're trying to save the turbocharger. You'll burn up the bearings, or essentially seize the turbo shaft by cooking the oil in the turbo by shutting off a hot turbocharger. And on top of that, oftentimes it will start burning up the seals. So you have that problem in there. So after you've been driving around hard, if you have a turbocharged vehicle, you want it to sit there and idle, 30 seconds, maybe to a couple of minutes, to let everything cool down and to get nice, fresh, cool oil to the turbocharger. Because of this, if you're installing a turbocharger, you might also want to install an oil cooler, because you're putting a lot of extra heat load on the lubrication system. You're heating up the oil extra amounts as well by the addition of a turbocharger. And lastly, I wanted to say that the seals in the turbocharger are pretty important. So if I clear out those drawings, and let's say this is my compressor wheel. So I'm going to write compressor right there. So there's my compressor side. And I have a little seal, little lip seal that comes on here on the compressor side. And of course that seal, he's keeping the oil back in here in the bearings, right? Well, once I start wiping out that seal, the oil in here is under pressure, and it can just come right past here, get thrown on the compressor side, and now I'm pumping oil into the engine through the turbocharger. So if you have a turbocharged engine that is smoking excessively, it may not be worn piston rings. It could just be a destroyed turbocharger oil seal, right? So again, as you add more crap to a vehicle, right, you increase its complexity. If I put a turbocharger on an engine, now I have one more part that can fail, and with the different ways it can fail, it can produce different complaints. Bad turbocharger seals are pretty common, and it usually results in the engine excessively smoking or consuming oil as it runs because it's sucking it through the turbo seals. So, and by shutting off a hot turbocharger, that's a sure way to not only damage the bearings, but start cooking those seals out of there. And that's much more so the case with this style of turbocharger than even like a centrifugal style supercharger, because you have all this heat from the exhaust system there that's cooking things out for you. So it makes the engine more efficient. There's a lot of extra plumbing that has to happen there. I mean, there's definite challenges that have to be overcome and compromises that are made when you turbocharge a vehicle. And those little turbo timer computer boxes I was showing you, those are kind of like a thing to automatically keep the engine running. So even if you space out and forget, the engine just doesn't shut off right away. It keeps running and pumping cooler oil up to the turbo. So my turbocharger components, right? I have my compressor wheel on the intake side. It's got curved fins. These fins are the opposite direction of the fins on the turbine wheel. The air is drawn into the center and it's forced outward by centrifugal force. And this airflow ultimately is what causes the boost pressure on the intake side, right? Okay. Selecting the compressor is pretty important, right? And so we can say selecting the right turbocharger, but specifically it's like, well, what compressor is on the turbocharger, right? What are the angle of its fins? What is what is its actual size? And that all corresponds to, what CFM, cubic feet per minute of airflow, does the engine need? How much boost pressure do we want to run in that, maybe we felt like our engine is built strong enough to handle 15 pounds of boost, but we don't feel like our engine's built strong enough to handle 25 pounds of boost, or we don't want to have to buy $10 per gallon race fuel to run that high of boost pressure, because we know that will impact what our dynamic compression ratio is going to be. So there's lots of reasons here as to why we would want to make sure that we choose the right turbocharger. If I go back here as well, and I look at this turbo, we talked about that delay or that turbo lag. Oops, not lag. That turbo lag, right? This is that delay time in between where we get on the throttle and then we actually achieve some boost pressure and we're having more power, right? And you can feel the turbo boost build and the power increase dramatically as this happens. And some engine designs will have more lag than other just because the length of the plumbing involved. Like I said, a ball bearing turbo is going to spool up a little quicker, so it's going to have less turbo lag. Generally speaking, though, the smaller the turbo, that's going to equal less lag, right? Because it can spin up faster. But it's also going to equal less boost. Right? If I go with a bigger turbo, the opposite's going to be true. It's going to have more lag time because I have a bigger device in there that I got to spin up. But I can get a higher total boost level, so I could achieve maybe more horsepower, but it's going to take me maybe longer to get there. So it's finding that balance. And this is where some cars from the factory had staged turbos where they would have a small turbo and a bigger turbo, and they would stage each one so to kind of broaden the engine's power range. So the other thing that comes into play, though, is so we know that the size of this matters as far as turbo lag, but we also want this turbocharger running as efficiently as possible. So again, the size of this thing is important for its efficiency. So this thing that's circled here, the size of the compressor, the angle of the blades, that's all important for the efficiency. And then on top of that, I can go through and I can change the housings. I can change the exhaust housing or the compressor housing for different responses from it. But you know, there's a lot to be said by picking the right compressor. So the next few slides are all about how do I pick the right turbocharger, specifically the turbocharger with the right compressor wheel shape that's going to be running efficiently for what I want to do with it, right? So we usually say, yeah, pick the right turbo. It's really a little bit more specific than that.
Don't you have a story about a turbo that was like way too big for a car on the diameter?
I do. I'll get to that one. I'll get to that story here in a minute. But I'll get it there. All right. So I have proper compressor selection is vital to turbo performance. Compressor maps with some basic mathematical knowledge, some math skills. That's going to help you determine the right compressor size, the right turbo for your application. Okay. We've talked.
I wonder.
Previously,
would it be possible to turbocharge the Fit Bike?
You'd have to have a pretty small turbocharger. Honda didn't make a turbocharged motorcycle, so I'll show. Maybe you can see. Okay, let's go through this and then I'll show you how you can figure that out, Nathan. All right.
Okay.
So you have to know you have to know the engine's airflow requirements, right? How many cubic feet per minute? So again, remember that this formula, we've actually looked at this formula before earlier on in the semester, where we took the cubic inches of displacement times the RPM times the volumetric efficiency we expected it to run, right? So at best, we're going to say a 2-valve per cylinder engine would be 85% VE. When I get to 4 valves per cylinder, maybe we're getting to 90%. Maybe if we have something with a really well-tuned intake and exhaust system, maybe we could be 100% or maybe just a little bit over at 105. But we'll plug in a volumetric efficiency number, okay? And then we're going to multiply that by PR, or the pressure ratio. And the PR pressure ratio, remember we've looked at that number before just a few slides ago, where we took the boost that we achieved and we add that to 14.7 and then we divide it by 14.7 and we get a pressure ratio. All right, so we take all that mess of equation here and now we're going to put it to use. Okay, so on my example here, what I've chosen is 4 valves per cylinder, 3-liter engine, so that's 183 cubic inches, and we want it to make maximum power at 6,400 RPM. And we only want to run 10 pounds of boost, let's say, because maybe we're trying to run, you know, not crazy fuel in this thing. Maybe we're worried about we don't have super good forged pistons, so we're trying to keep the boost levels at 10,000 or 10 pounds of boost at 6,400 RPM. So what do? Well, we figure out the pressure ratio by this formula, and it comes out to 1.68. Then we start plugging stuff in. Remember, this is 4 valves per cylinder, so we're going to say it's got 90% volumetric efficiency. We multiply all those things together, divide it by 3456, and we come out to the engine wanting 512 CFM cubic feet per minute of airflow at that 6,400 RPM level. If I wanted if I had engine specifications, like in this case, we had a 3 liter, and it's like, well, how did I get 3 liters to 183 cubic inches? Just multiply liters by 61, because it's 61.02 cubic inches equals 1 liter. How I got from here to there. Anyways, this tells you the airflow requirements of the engine. That's going to be important because I need to know how much air the engine needs so I can figure out what turbo is going to pump the right amount of air for what I need, right? So let me clear those scribbles. And so if we did this again, but let's say we wanted to make sure that, you know, at 3,000 RPM, this thing was pulling strong. If I did it again, you could see that it comes out to roughly, you know, not roughly, but exactly half of the airflow. So it's a pretty linear deal as far as the way this equation works. So ideally, we would want a turbocharger. If we want the engine to run good, have a good, strong, broad power band, we would want a turbocharger that could efficiently deliver 200 CFM as well as it could deliver 500 CFM, right? Okay. Okay, so we got the CFM number. We know that we want 10 pounds of boost. And we know what our pressure ratio is with that. And we got our numbers now. We got the 256, the 512, we're running 10 pounds of boost, 168 pressure ratio. Now we got the numbers that we need to figure out what turbocharger, specifically what compressor on our turbocharger we want to suit our application. And to do that, we have to look at a compressor map. So that's what we're going to do right now, is we're going to look at some compressor maps. I guess I should say, how do I get a compressor map? Well, let me just switch this to my screen and I'll exit out of here. If I have this on your Canvas page now as well, but basically I would look at a turbo catalog, right? So Garrett, Air Research, like different turbo companies, they'll have a catalog, and inside the turbo catalog, and actually you guys tell me, can you guys see this turbo catalog right now on your screens?
Yeah, we can see it.
See it? Okay, okay.
I was wondering, does Texas Speed make turbos?
Texas Speed.
I don't believe.
That name doesn't ring a bell to me, but
I really don't.
It's more for drag racing.
You know, you have Garrett, Air Research. So one of the things I found myself, I say it a lot for my engine class, and I want to tell you guys is you can learn a lot by reading catalogs, right? So in engines, I say, hey, read the bearing book, read the bearing catalog. You can learn a lot about engine bearings and how to choose the right bearings for your engine, all that type of stuff. This Garrett turbo catalog, you can see that it's got a lot of good information here about how a turbocharger works and how do the ball bearings affect things, and then what are the wheel measurements. And this thing right here, that's a turbo map. And it even tells you in the catalog how to read the turbo map and how to figure out your AR ratio, right? That's area versus radius of the housings, and we'll get into that. So there's a lot of good information, and if you go through here, and this is where Nathan, you were asking me about picking a turbo for your pit bike. Well, go through there. If you knew the displacement of that engine, and you did the formulas where you figured out, okay, well, this would be its volumetric
efficiency. 49 cc's.
This is the airflow requirements. Then you could use the catalog to see if you could find a turbocharger that would match that engine, right? And you see how in this catalog, every turbocharger, they give you a compressor map, and then there's different numbers and stuff in here. So that's where we get these compressor maps. Okay, so
I'm wondering,
Go ahead.
Since it's already like a Honda clone engine, I wonder if it might be easier just to get, say, like a Honda Monkey engine, because I know you can get those in like a supercharger kit instead.
Yeah, it very possibly might be. When you're picking your own turbos out of the catalog, like you are the engineer, right? You're engineering what you want to happen. And you buy, they've already selected or built the right parts and selected the right turbo for what you're trying to do. Okay, so remember, here's where we're at. We figured out all of our numbers for this 3-liter engine that's going to run 10 pounds of boost. And now we're going to look at our turbo map. So this would be right out of the turbo catalog. Okay. So what's going on this map? And again, the front of the turbo catalog will teach you how to read this as well. But so these numbers on the compressor map, they don't actually put these turbochargers on engines to make these maps. These are all done in a test lab as they're flowing different airflow amounts through the turbocharger and measuring pressures and stuff. So they're tested in a very lab type situation. All right, what do those numbers mean? Well, they indicate the RPM of the turbo. So remember how earlier I said, hey, a turbocharger can go well over 100,000 RPM. Well, there you go. Here we're at 153,000 RPM here. So those numbers are turbocharger RPM. These numbers that are represented in these different circles indicate the turbocharger efficiency, right? So the turbo gets the most efficient in the center, and it's getting over 70% efficient. And then it gets, you know, a little bit less efficient and a little bit less efficient as we start moving out further and further away from that center point, right? So if I want an efficient running engine, something that's going to run well with this turbocharger, I want to pick a turbocharger and keep that turbocharger running in its most efficient operating range. All right, so those are turbo efficiency numbers. So the closer we get to the center of the bullseye, right, the more efficient that turbocharger is. All right, so now we have some other numbers here, okay? These numbers represent the pressure ratio and the pounds of airflow per minute numbers. So these are our airflow numbers, and the pounds per minute is how do you figure out what your pounds per minute, right? Because we were talking about cubic feet per minute. And so how do we convert it to this number down here? Well, to do that, what we would do is we would divide the CFM that we calculated before by 1427. So CFM divided by 1427, that'll give us these numbers along the bottom side of the scale. The pressure ratio, we've already figured out that data. Okay, so now, so what are the pound-feet per minute? We're dividing it by that 1427. Well, we take our 256 and our 512, and we divide it by the 1427, and we end up with 17 and 35.9. And so what that means is that our turbocharger, based on our calculations, we need the turbocharger to run over in this range and over in this range, and we're totally off the map, right? We're way off the scale. So what does that mean? Well, that means we picked the wrong turbocharger. This turbocharger is way too small for our application. Okay, we need to pick a bigger turbocharger based on our engine specifications and what we're looking to do with that engine. Okay. There's one other thing to point out here on this compressor map, and that is this surge limit line. Okay, so if you pick a turbocharger that's too big, you're likely going to have a turbocharger that is not very stable. It could be damaged when it starts to build boost and then comes off a boost. So if I pick the turbocharger that's way too big, first of all, what I'm going to have is a lot of lag time. And Luke mentioned I had a story. I actually had a student that brought in his Supra, and he had put just a giant turbo off of like a diesel semi-truck on there, and he had cobbled it all together. It was very much a homebrew, Home Depot cobbled together system, but the turbocharger was huge. And so what you ended up with was a ton of turbo lag. In fact, what he said is he goes, man, I put this on the car and it runs slower than it did before. It just takes forever to get going. So we put it on our old Clayton dyno, because at the time we didn't have a horsepower dyno there. We just had the old Clayton, and we, strapped it down and romped on it, and it's sitting there at wide open throttle. And this thing, it sat at wide open throttle for like a clear, 62 seconds before, and we had a pressure gauge taped to the intake manifold so we could read the boost pressure. So it took a full 60 seconds of running at wide open throttle on the dyno before it started to build up any boost. And then at like 63 seconds, we got like 2 PSI of boost. And then all of a sudden the boost started just dramatically increasing, so much to where I saw the boost pressure just start jumping up, and it went past 10, and the car started to burn out on the dyno and got all squirrely, and so we had to get off of the throttle. So he ended up where he had a turbo that was really down here on the surge line.
What was the size of the turbo?
And then it just started surge. I don't remember how big it was, but he actually got it off of, like, his uncle was a truck driver and had his own truck, and so it was off of a diesel semi truck, and I think it was a big Garrett or something. But he cobbled it all together, and the exhaust system was all compromised, and I mean it was a pretty ugly
for a little 3-liter 6-cylinder.
Exactly. It was just way too big. And so what happened is it had tremendous turbo lag. When you finally got it to spool up, it spooled up like crazy. But driving it around, he could never be wide open throttle anywhere long enough before he'd have to get out of it, right? Imagine driving you're at wide open throttle for a full minute. Man, it's not gonna happen. So he just had way too big of a turbo on there. And ended up with a car that really wasn't drivable at all. And what would happen is this turbocharger would experience huge surges as the pressure built and then dropped off. And of course, it would build up pressure really fast because the turbo was such a big pump for the engine that the boost pressure would build really fast and then surge back. So anyways, you pick a turbocharger that's too big, that's not going to work well either. You're going to be playing around here below the surge line, and that could even damage not only your engine, but damage that turbocharger as well. So, all right. So with this, what we're going to find is that if you're below the surge limit, you're not going to get full boost. We're going to try to pick a turbo that works better for us with the 3-liter engine that we picked for this example, right? So here we have an Innovate turbo, and we'll see that when we start plotting things out, the numbers that we got before with the 256 CFM and the 512, when we start dividing those out, and remember that the numbers that we had got were 17.9 and 35.9. So if I take the 17 and the 35, it puts us there and there. So this is pretty darn good, because even at the lower RPM, although we're not in the most efficient operating range of the turbocharger, we're still on the map. We're still above the surge line. And then at maximum RPM, at our 6,400 RPM, we're going to be right in the sweet spot of this turbo at maximum efficiency. So we're at maximum turbo efficiency where we're expecting to make maximum power. And so this turbocharger would work much better for our engine application, where we want to run 10 pounds of boost, and we want to run that 10 pounds of boost at 6,400 RPM. And you can see that the compressor speeds have come down a little bit, so they're a little bit more reasonable. So, there's a lot of importance to picking the right compressor for your application, okay? And so I had a whole activity that we would do, but after talking to some of you guys, I'm gonna do this activity as a extra credit thing where, and I'll show you how to do it, but where you can use the Garrett catalog and pick a turbo. Remember, you don't want one that's too big, but you also don't want one that's too little, because then that's going to not give you good, the full potential of your engine, in that it will not make as much boost. It can be exhaust restriction. Yeah, go ahead.
Charlie had a question in the chat, is what I was saying.
Oh, Charlie had a question on the chat. Okay, I'm firing up the chat. Okay. All right. So on the Supercharger, the vast majority of your Superchargers do not share the oil in the Supercharger between that and the engine. So the oil that's in the Supercharger in that front little gear set, if I get back to a better picture, this oil right here that will be stored in this gear set, it's not connected to the engine oil. It's its own special oil that just runs in that little housing. And periodically, you should change it out of there. Now, some Supercharger manufacturers, they'll say, oh man, it's lifetime fill, but I would change it out of there, around.
He put in the chat that he meant turbo.
Oh,
yeah, tomato
right. So Superchargers, change that oil maybe every 60,000 miles. It's a different oil than your engine oil, okay? All right. But on a turbocharger, the way the turbo is plumbed and located, if I can get, there we go. As soon as you shut the engine off, the oil outlet's always at the bottom side of this, so it should just kind of normally drain out of there. You shouldn't need to rotate that thing at all. But what I would do is I would not drain the oil out with the thing really, really hot, but I also wouldn't want to drain out the oil when it's really cold. I would take all my good oil changing tips where I would have the engine where I've driven it. It's warmed up so the oil will flow out easily, but it's not so hot that it's going to burn us or anything if we spill any. But that way we'll get most of the oil out and then fill it with fresh oil. And when we start it up, we wouldn't want to, go to high RPM or start boosting it right away. We would want to let it run a little bit, let it circulate, let it pump fresh oil to the turbocharger. And then we could start driving it spiritedly. So yeah, good question. You don't have to spin it or anything. It should drain out of there fine on its own. What you will find is that when it comes to oil change intervals, a turbocharged vehicle is usually going to ask you to change the oil more frequently than a non-turbocharged vehicle, because as you can tell, we are definitely putting more strain on the engine oil to cool that turbocharger, right? We're putting more heat into the oil. We're having more shear loads on the oil. So if I have a turbocharged vehicle, I definitely want to change its oil more frequently than I would on a naturally aspirated vehicle. So if you took two cars from the factory, you had your first car was the base model, and it might say change the oil every 7,500 miles, and then the turbocharged model would probably say change that oil every 5,000 miles. And I would say if you're really running it hard, you'd probably want to change that oil every 3,000 miles, right? So, yeah, good question. All right, so we beat you up with the compressor maps. Pretty good. The turbine side can also be selected because that impacts how the exhaust gases hit it, which will determine how quickly it will spool up. With that, on top of that is we want to know not just what's going on here with the actual turbine, but what about the housing around the turbine, okay? So when it comes to turbine selection, it's the housing is a big deal. So extruder, the bore diameter, the exit of this turbocharger, this diameter is important, right? Smaller openings here, well, that's going to give you higher exhaust velocities, so it'll generate more back pressure. It'll also boost quicker, but ultimately it's going to restrict flow. So if this exiting path to the turbo, if it's larger, it can support more horsepower because it can flow more exhaust gases, right? But you're going to lose some low to mid-range power because you're going to end up with more turbo lag time. So I can actually, I can change the way the turbo is going to behave a little bit by changing the AR ratio, which stands for area to radius, basically the turbine housing. So if I know it's hard to see, like you can see that this one doesn't have any housings on it, right? Which you might not realize. I'll turn my camera on here. There we go. Is that if I have a turbocharger here, if I zoom out, so you can see that here's where oil would go in and out of the turbo. There's coolant passages. So this turbo is not only lubricated with oil, it has some water cooling that we plumb to it as well. But this thing unbolts in that I could undo these bolts on this housing here and basically change the turbine housing on this turbocharger. While I got this thing up on the screen, here's my wastegate, right? That's how I can control how much boost pressure this thing makes. You also notice that here's the turbine blades, and then you can see the shaft and this little nut on the end. And you guys notice how that the top of that nut's kind of like ground down, kind of weird? Well, that's the turbocharger as it gets assembled. Remember, it's spinning at 100,000 RPM. This thing has to be precisely balanced. And so it gets actually spun up on a special balancing machine. And then they figure out where it's heavy and grind metal away to get it properly balanced. The bigger amount of material removed, the more like chunk you see out of there. Like it's got a pretty big chunk. That means that this thing was pretty far out of balance, and they had to remove quite a bit of material there to get that turbocharger balanced out properly. Well, the reason I brought this up on the screen was just to kind of show you how this guy's bolted together. So if I undid the bolts, this housing would slide off. Other like performance turbos for racing applications, these could be held together with bands so they can be changed quickly. But if I change this housing here, it will affect the way the turbocharger makes boost. I can make it boost up sooner or later, so I can decrease the lag time, but I have less less boost overall. So I have less turbo lag, but less boost. Or I could have more turbo lag and I can have more boost by changing the size of this housing. And that size, we commonly call it the AR ratio. So, could you guys see that turbocharger on your screen?
Yeah.
Okay, good. Just got to make sure I have the right screen share options going on. So I know it gets kind of complicated, but it's cool. I've had the opportunity to do this where we changed housings, and it was almost kind of like changing a camshaft or something, because you could change where the power comes on. So to explain the AR housing, it doesn't look like what it is here, but this thing is rolled up like a snail, right? It comes in and it goes around like that, and then it goes out, right? So it's like a big cinnamon roll or something right in there. So if I take that cinnamon roll and I unroll him, he's going to be a straight tube like that. So that's what I'm going to do in my next slide, so you can really understand what's going on with this housing. All right, so if I have an AR ratio, if my housing AR ratio is numerically high, basically it's bigger here, right? This thing is physically wider, okay? So it's got numerically high air housing ratio. It's going to be able to flow more exhaust gases in and out of the turbo. If I have a smaller AR ratio, it'll flow the exhaust gases in, but they get more of a restriction as they actually get to the turbine wheel inside the turbo, right? So I might have a 0.8 AR ratio, a 0.6 AR ratio, and that's the ratio of the area versus the radius of that housing. Or if you want to think of it real simply, it's like the size of the housing, right? So what does that do? Well, high AR ratios, all right? Less back pressure, more torque, right? More horsepower and torque, because I'm going to have more boost pressure, but I'm going to have more lag time. So it's going to take longer to boost up, okay? So if I want to have boost sooner, so let's say I was autocrossing a Subaru WRX, and I've autocrossed a Subaru WRX, and it was extremely frustrating because it wasn't the STI, it was just like the stock WRX. And you get on the throttle and you wouldn't really start building up boost pressure and making some good horsepower till almost right before you had to get off the gas to brake for the next corner coming up, right? So you really weren't able to take advantage of the boost that engine could make, and it was really frustrating. I would want the boost to come on sooner. So what I could do is I could pick a different housing if one was available for my turbo with a lower AR ratio, and that would give me boost sooner without having to change the whole expensive turbocharger, right? So that would be the advantage of that. So like you're tuning the turbo by what housing you picked for it, right? So kind of a neat thing to do. All right, so low AR ratios, more velocity, less lag time, but ultimately they're going to be a restriction. So you're going to make less boost, right? You're going to have less boost being produced by that turbo, but you're going to have more boost lower in the spectrum. So it's a way that you could take a turbo. Maybe you got a turbo that's maybe arguably a little bit too big for what you're trying to do, but you could put on a smaller AR housing, or maybe you got a turbo that's a little bit small, but you could put a bigger housing on there, and so you could play with that turbo by what housing is on it. Okay, We've already talked about the shaft. I kind of beat you up about that. And ball bearing versus this is a standard bushing turbo shaft, right? The ball bearing is going to spool up quicker. It's also going to be more expensive. We talked about the turbo seals. The wastegate, I just showed you a wastegate on this turbo. So basically how that wastegate works, and here's some good shots of different turbos and their wastegates, is we control how much exhaust flows through the turbo. So remember that the exhaust gases, they flow in, they go through the housing, and then they go up to the turbine, spin it, and then they flow out, right? So here I have an integral wastegate with the housing. So here the wastegate is closed, it's flowing through the turbo. If I want to limit my boost pressure, I'll just limit the speed of the turbo to do that. And so when I open up the wastegate, the exhaust just goes right out the wastegate, and therefore bypassing, I end up with less exhaust gases going through the turbo. So that lowers the speed of the turbocharger turbine wheel, which of course is going to lower the speed of the compressor wheel, and it's going to lower your boost levels. So this one in this turbo, this Garrett with this housing where it's got an integral wastegate, that's more what you'd have in a normal stock configuration, right? If I was going something crazy all out race, well, I'd have something like this where I have an adjustable wastegate that I can control. I can change the spring inside the wastegate. He's kind of plumbed up separately here from the housing, and he does still control an exhaust bypass. So he controls turbocharger, but again, it gives me more tunability with the turbocharger because I can control the tension of the spring on the wastegate, right? Now, if it's just capped off like this one is here, then maybe it gets to, let's say, 20 PSI, and at 20 PSI, this pushes up this valve, it opens it up, and then we thereby limit our boost pressure to 20 PSI. If I have a hose fitting on this, I can plumb this hose fitting back to the intake manifold, and I can utilize intake pressure to help us control when the wastegate is going to open up. So that's how we control what our total boost pressure is going to be, by controlling the speed of the turbocharger by a wastegate, which essentially sets up a bypass passageway around the exhaust side of the turbo. And just like it said in the video, let's see if I. Well, just like it said in the video, most vehicles from the factory these days have computer controls on the wastegate, so they can control how much pressure actually gets to the wastegate. Now, in the racing world, the aftermarket world, as you can see by the screenshot here, you can also control the pressure going to the wastegate, and then thereby controlling the turbo directly. So they have electric solenoids with electric boost controllers that you can program different settings, right? Race gas setting, pump gas settings, so I can control boost pressures depending upon what fuel I'm going to run. That's also something that the Haltech or a Motec computer could control. I could have a manual boost controller where I'm manually controlling how much boost pressure actually reaches the wastegate. You know, if I just disconnect the vacuum line from the wastegate, it's going to go to its default. Its default will be whatever spring pressure is in the wastegate actuator, right? Which is usually going to be higher than what you'd want if you're running, you know, pump gas. But anyways, so controlling the wastegate is how we can control what our turbo boost pressure is going to be. And most cars moving from, you know, the 70s and 80s to today, they'll control turbo boost pressure by controlling the wastegate. So there's a manual boost controller, or I can control the knob. I can do it electronically. I can program it in there. So we're getting there, right? So far we've got our turbo. We've selected the right one for our vehicle. Maybe we picked the right exhaust housing for our vehicle. Now we've got a wastegate there. That's going to control our boost pressure, but we're not out of the woods yet. We still have more controls on this thing. And those controls also have to include a blow-off valve. So what is a blow-off valve? Well, you can see this thing opening and closing here. The blow-off valve is the thing that if somebody has a turbocharged car and they get on it and then they let off the throttle, it goes, it sets that big surge of air, that noise that you hear. That's the air blowing off the pressure from the blow-off valve. So what does it do? It reduces pressure in the intake tract when the throttle is released. And what that would do is help prevent shocks from going to the compressor wheel and possibly damaging the wheel. So whenever you have a high amount of intake, a high amount of vacuum in the intake manifold because you've closed the throttle really quickly, that is going to be directed, that vacuum is going to be directed to the blow-off valve. And what the blow-off valve is going to do then is he is going to open up and he's going to dump the boost pressure. And in theory, that keeps the turbocharger from slowing down as much, and it reduces the amount of shocks to the turbocharger. And as a side benefit, it just sounds freaking cool, right? So I remember when I first started teaching high school, I had a young lady in my class, which later went through the program at ARC and became a master Toyota tech. And last I saw her, she worked at All Data and all kinds of stuff. And she had a little Mitsubishi Eclipse and put a big old blow-off valve on there. I think the car was all stock other than the blow-off valve. But she got more attention with that car and that blow-off valve from all the boys in class because it sounded awesome. You would let off on the throttle, and this is kind of what she had here. She let off on the throttle, and this thing would just dump the pressure in the intake, the atmosphere, and it'd make that loud noise. So that's your blow-off valve. Now, even stock vehicles from the factory that have a turbocharger, they will have some type of blow-off valve. It's just not going to vent its air to atmosphere and make a bunch of noise. It's usually going to direct this back to like the air box to act as like a muffler so you don't hear the noise that's being expelled from the airflow, but they'll still have some type of a blow-off valve because it does help protect the turbocharger. So with the turbocharger, you have a wastegate to control maximum boost pressure, but you also have a blow-off valve to basically prevent shocks on the turbocharger and prevent damage to the turbocharger. That also, in theory, keeps the turbo speed up. So if I put this diagram back on the screen, it actually has the next thing on there that we're going to talk about is the intercooler. But let's add some stuff here. So what we would have here is let's see here. I gotta get my drawing tool up. Right. So we would have our wastegate, which would be like a passageway around the exhaust side of the turbocharger, right, to control the boost pressure. And then the blow-off valve, if I put him, I could put him over here, I could put him over here, I'll put him right there. He's gonna have a vacuum line on him. What I don't see in this diagram is I don't see a throttle body. So I got to add that throttle body in. I'll add him in right here. So I'm going down the road and I'm at wide open throttle and I'm making all kinds of boost pressure, and I'm happy. And then I got a brake for the corner coming up, right? So all of a sudden I go from wide open throttle to closed throttle. So now the throttle closes, the turbo is compressing a bunch of air, and now it's ramming against the closed throttle. Uh-oh. Well, what that's going to do is it's going to build up pressure back, and it's going to shock the turbo, and it's also going to try to stop the turbo from spinning, right? So it's going to slow the turbo speed, put shock loads on the turbo. Well, when I close the throttle, the engine's spinning still really fast. So this goes from a pressure to all of a sudden, now it's got a vacuum inside here because the engine's spinning against a closed throttle. So I take this vacuum and I direct it with the vacuum line to my blow-off valve. So when I close the throttle, I make a bunch of vacuum in here, that this excessive pressure now that's built up inside here, that can be blown out of the blow-off valve and expelled to the outside. And that will kill the shock loads off of the turbo, so its RPM stays up. So as soon as I go to come out of the corner, I hit my apex, I roll on the throttle. The turbo's not now at 10 RPM. It's still spooling up at maybe a 50 or 60 RPM, 50 or 60,000 RPM, and I'm going to spool up quicker and have less lag. So that's why you'll see a blow-off valve on there, even on vehicles.
Would there be a reason for a blow-off valve on a naturally aspirated vehicle, though?
No, not really. A blow-off valve on a naturally aspirated vehicle would make it not decelerate, right? If you let off the gas and all of a sudden that valve opened up and let air in, it would surge. Now remember that the superchargers, they have kind of a blow-off valve in that if they had a backfire, they would have a valve that would blow off to let out excessive pressure to not damage the supercharger, right? And you can have some superchargers that have kind of like a wastegate type of thing where they can direct some of the compressed air. They can direct that basically back out to blow off excessive boost pressure. So you can have some boost controls on a supercharger. So anyways, hopefully you're getting that. One, yeah, turbochargers are awesome, but two, there's a lot of complexity there, right? There's lots of parts and pieces that you've added to the engine to make this work. That being said, turbochargers are getting a lot more common because they make the engine more efficient. And so if I turbocharge a vehicle, this is how I can get, 40 plus miles to the gallon with direct injection, because I'm making that internal combustion engine more efficient with that turbocharger. All right, intercoolers. We just saw that little diagram of that intercooler. Remember, as we compress the air, it gets hotter, and that means the air is less dense. So some of the benefit by compressing it is lost as we heat the air up. Also, the heated air is much more likely to get us into a detonation mode. So the purpose of an intercooler is it does add some plumbing. Excuse me, it does add some plumbing to the intake system, but it's going to make the air cooler, and that makes it more dense, and air that's more dense contains more oxygen, which is really what we want in the combustion process. We don't just want air, we specifically want the oxygen in that air. So plumbing, we're talking about the hoses and different components and all that type of stuff. So here we can see some good examples of plumbing and intercoolers, and I chose this particular setup because this is our Nissan or our 350Z or Infiniti G35. This is that 3-liter V6 that's in our G. And this is a turbocharged kit that's on there. So you can see the nightmare plumbing situation of this thing, right? It's got the 2 exhaust manifolds running through the twin turbos. Then it has twin air intakes feeding each turbo. Then the turbochargers, they dump their air out and route that through the intercooler. Air goes up through the intercooler and then ultimately into the intake manifold. So you can see like that system looks pretty sweet, but there's a lot of plumbing on there, right? Like here's the air leaving the turbocharger. It goes up and then down and then to the intercooler. On the other side of the engine, it's doing the same thing. The air is going up and then down into the intercooler. Here you can see on each side, like here's the wastegate for that turbo over there. You can see the oil line over here. So there's a lot of plumbing that comes in the place of this system. But that's a great shot of the intercooler. Now, what's the idea here? As I start compressing the air starts warming up in here, right? But as I'm driving down the road, right, I'm driving past maybe some cooler air going down the road, and so it's going to blow through the intercooler, which is essentially like a radiator, that the air flows through, and that can absorb some of this heat and pull it out of the air as it goes on its way to the engine. It does.
Would there be a reason for an intercooler on a naturally aspirated vehicle? Would it work still?
Yeah. There's some. Anytime you can have colder air entering the engine, that's going to be an advantage. Okay. And there's even intercoolers that, you know, they spray water on there. So this is an air-to-air intercooler. There's air-to-water intercoolers. Supercharged vehicles can have intercoolers. It increases the plumbing length. It increases the distance between the turbocharger and the intake valve of the engine, which just that increased distance does increase lag time. But the advantage of it is that you get colder air. And so even at the same boost level, you're going to make more power with the cooler air than non-cooled air. So you're going to get more power from the same level of boost. So intercooler is a big deal. I've even seen intercoolers where guys are blowing nitrous on top of the intercooler to get it to cool the air entering the engine. Any type, even on a naturally aspirated engine, if you can get that engine to draw in cooler air, it's going to make more power. Now, if you can imagine that this intercooler inside here, essentially it's like a radiator, right? So your question was, well, could I put this on a naturally aspirated engine? Would there be some benefit there? There very possibly could be if you're getting colder air in the engine. The downside is, if you look at this, is that these guys are kind of restrictive, right? So if I don't have a turbocharger or a supercharger forcing the air through this thing, whatever benefit I gain from this intercooler, I would likely lose due to the restriction and airflow that it creates, right? So that's the balancing act, is an intercooler that works efficiently, but it also is not a restriction to airflow. So intercoolers are there to try to cool that compressed air before it enters the engine, to make the air more dense, have more oxygen in it. That being said, it again adds more complexity, it adds more plumbing, and you know, there's compromises there. I mentioned the water to air style intercoolers, right? They're similar, except that they're going to circulate water around that thing. Obviously, they can have a real great cooling benefit for short distances, but they only work well when the water is cold. As the water heats up, its efficiency goes away. If I want to package an intercooler in a real small space, though, this is a good way to go. All right, so here's an example of a water to air intercooler design. So we're using the water to aid our temperature transfer. Again, you can see, hey, there's some complexity there. So now all of a sudden the intercooler, hell, that thing got complicated. Here's an air-to-air intercooler. These big intercoolers, if they have good airflow, they can reduce the temperature of the air a whole lot. And remember, every 10-degree drop in air temperature can increase the engine's performance by 1%. So that can be a pretty big increase in performance by running an intercooler. So oftentimes it's worth the extra turbo lag to have the intercooled because you're going to make more power, right? So it's all relative. You still have to package and plumb this thing, so you still have to overcome those challenges. So that's why you'll see a lot of cars, maybe from the factory, they don't have an intercooler because they just didn't want to pay for the packaging and all the plumbing of all that stuff. And then other designs will have intercoolers. So.
All right. It's like upgrade your car and stuff like that. You can actually buy like turbochargers.
I don't think we're catching any of that. It's sounding very.
Yeah. Hey, Jonathan, we're having problems with your connection. Try it again, or I'll punch up the chat. Type your question in the chat, okay, Jonathan? Because I can't make out what you're saying. Unless you all unmute you if I can here, and we can see if that that works. No, all right.
While we're waiting on him to type the question, I did have a question.
Yeah.
I sent an email to TUSO to ask if we still have to do CDX work and FCA work in the engine repair class, and haven't gotten a response. And I don't know if we do have to do that, or if we just come back and run the engine in the fall and we don't have to do the other work.
I'm not sure. I'll have to get with him. I'm sure we'll figure out something. I expect you'll have to.
Yeah, because the semester is about to end, and I don't know what to do about that. All that stuff.
You don't have to do anything. Now, when we come back to school, you'll be able to. We'll do a petition, and on that petition, I'll get with him, and he'll come up with what do you need to do. He might say you have to do CDX activities 1, 2, and 3. Take the final exam and fire up your engine is what I expect. And
so I won't need to do the homework right now.
I don't know. It's kind of up to him. I'm sure there'll be some of that involved, just like you were in the class normally. I mean, essentially what his job would be is to figure out something that would be relatively comparable to what you would have done in the class, right? Okay, so let's see, Jonathan. I don't see your question yet, Jonathan, but oh wait, from Jonathan. Oh, okay, yeah, you can buy different intercoolers and turbos. Those intercoolers have different amounts of horsepower and turbo and PSI. Is that realistic to what an intercooler does? A intercooler that is more efficient at controlling the temperature of the air, you could effectively run more boost because you're cooling the air more, and if you keep the air a little cooler, it's going to keep you out of detonation zones, right? So with a better, more efficient, usually a larger intercooler, I can get away with running more boost, and I can get more horsepower from that. That might lead to an increased amount of turbo lag, though. Also, you got to look at how well does the intercooler flow the air, right? And an intercooler that is very restrictive is going to then negatively impact the power that the engine can make, right? So yes, the intercooler itself can definitely affect the horsepower that the engine makes. And a better, usually a larger intercooler is going to allow you to make more power because you'll be able to run higher boost levels. Good question. Hopefully that answered it for you. So when it comes to turbochargers, the oil supply system is really important. One of the things I found is that people don't change their oil enough. And then manufacturers sometimes will do things that sounds good in theory, and then it becomes a problem. Like, for instance, Subaru, right? The WRXs are all turbocharged. It's really popular. There's a little filter screen inside the turbo lines. The turbo will fail. Somebody will put a new turbo on. They don't remove that oil filter screen, and they put the new turbo on, and that one fails because it's not having enough oil flow. So lubrication system is super important on a turbocharged vehicle to have a good fresh supply of oil to the turbocharger. Okay. Oil lag. We were kind of talking about this earlier because we were talking about oil changes and stuff, right? Well, I have on here oil and filter changes should be done at recommended intervals, right? If you put a turbocharger on a car that didn't originally have it, now you're going to be changing the oil more often, right? We talked about the oil coking up, and that's why you should let it idle down and cool off the turbocharger before you shut the engine off after you've been driving around. You know, if you've been driving around and you've been having that turbocharger make some boost, it's generated some heat, and you definitely want to cool that turbo so you don't cook up the oil that's inside there. And then I was looking for this earlier. Here's my oil and filter tips, right? So I think Charlie had asked the question, should I turn it by hand? You don't really have to do that, but it wouldn't be a bad idea to disable the ignition, crank the engine over a little bit until you get some oil pressure on the gauge. Now you know you have oil pressure to the turbocharger, and you're not going to be starting up a dry turbo.
Yeah, that's what I meant. I didn't mean by turning it over by hand.
Oh, okay. Well, look at that. You were on it. Most of the time with factory cars, like we don't do that, even that stuff. Just if you start it up, just, you know, don't run it hard. Let it idle for a while to get nice fresh oil up to the turbo before you're putting it under load, right? Because turbos are activated by load, right? The more load you put on the car, the more you open up the throttle, the more exhaust flow it makes, the more boost you're going to get from the turbo. So these two things feed back and forth. So just don't go boosting that thing until it's had a while to run and get a good supply of oil to the turbo. 20 seconds is what most manufacturers recommend. But you know, if you've been really driving it hard, you might want to wait a full 3 minutes. And this is where I clear these drawings. This is where we saw that picture of the turbo timer again. So now I need to share with you my turbo timer story, okay? I had a student who was working at Roseville Toyota, and he was working on somebody's, I think it was like a Celica or something, but it was turbocharged. They had put a turbo on there, and they had put a turbo timer on there. He goes to change the oil. He drains the oil out, fills it with fresh oil, and starts up the car, and he's got an oil leak because he double gasketed the filter or something. He shuts the car off because it's spilling oil all over the ground, and unfortunately, it had this turbo timer on there. He didn't realize it. There's a button you could press right here to disable the turbo timer. He didn't do that, so he shuts the car off. Well, it doesn't shut off. It keeps it on another 12 and a half seconds or whatever this thing was programmed for. So he's, you know, trying to frantically shut off the car. The car won't shut off because of the turbo timer wired in there, and it's spilling oil all over the ground as it basically pumps the oil out of the car. Luckily, at Roseville Toyota, they had an oil system that was out of a gun. So the guy on the top of the car, he put the gun in the valve cover and just started filling the car. So he was spraying the oil into the engine as fast as it was pumping out of the engine. So the engine didn't starve for oil, but they probably wasted a dozen quarts of oil in the process. So if you're going to do an oil change on a turbocharged vehicle that has a turbo timer, you would want to disable the turbo timer before you go to start that car as you're doing your leak check and stuff, right? And usually when you're servicing a car with one of these on there, you'd want to put it in its standby mode so that you're not fighting that turbo timer all the time as you work on the car, okay? So turbo timers are cool. They have their place, right? Because they help prevent you from cooking your turbo. But in the service lane, that can be a real problem. So, all right. So now we're getting to the end of this thing. Turbocharger inspections, right? As I said before, they're dependent upon exhaust flow, right? So if let's say you had an engine that was smoking or something, right? I have here check cranking rhythm. It's like, you know, you want to determine, is this a compression problem or is it a turbocharger problem, right? Take off the plumbing on the intake, see if there's a bunch of oil up in the intercooler. That would indicate a leaking turbocharger, right? If you don't get the boost, levels that you're looking for, you know, check to make sure that the throttle is going to wide open throttle. While you're running the engine, throw a vacuum gauge on there. You can check the vacuum while it's running, and then it should rise when you do a deceleration. That checks the integrity of the intake system. And then you can use that same gauge to check what the turbocharger boost pressure really is. So noisy operation. I've seen the exhaust turbines completely melt down due to the excessive exhaust heat and burn up the turbo and get wedged in here so that you couldn't spin the turbo at all. I've seen carbon buildup, lack of lubrication. I mean, all kinds of things. Some of these turbos, they create so much heat that they just burn themselves out. So usually a lot of your turbo problems you can find with a good, thorough inspection. In fact, what I'm going to do right now, okay, good, I got the screen up, is I'm going to switch this over to the document camera. If I'm looking at my turbocharger, well, this one, it's missing its compressor wheel here. Sometimes you'll see something where, like, well, Jared on his Honda just the other day, his air filter came apart and his turbo sucked in bits of his air filter and it kind of chewed up the blades on the compressor, right? So you can have damage on the inside of the compressor. What I see a lot, though, is that these blades on the turbine will start to get melted down. While you have the turbocharger off, move this around and see how much play you have in the bearings. If you have a bunch of up and down play, like I have right here, that's a sign that you have bad bearings in your turbocharger. This should have a little bit of play, but it should feel relatively smooth and not so much play that you can move it and the turbo starts scratching on the housing. So this one's got too much play inside, which is probably why it became one of my show and tell turbochargers. So a good thorough visual inspection, that's what's gonna help you diagnose a lot of turbo issues. If I look at the exit of the turbocharger here, there's a bunch of oil inside here that's telling you the seals are leaking. And again, remember that most cars from the factory, they have really crappy boost pressure gauges. They keep the boost pressure gauge kind of abstract on purpose, so you can't really tell how much boost pressure you really have. A good vacuum pressure gauge will not only allow you to see how much intake manifold vacuum you have, but it will also show you, a limited amount of boost pressure. Now, this particular one would only go to 10 psi. For a lot of factory cars, right, that came from the factory with a turbocharger or a supercharger, that might be plenty enough to see if it's making the proper amount of boost. They also sell these that go up to about 15 PSI that allows you to really monitor what the boost pressure is. So if you think, hey, I'm not making boost, hook this thing up to the intake manifold vacuum, intake manifold port, and go drive the car. When you're just cruising down the road, you're probably going to have some vacuum on here. But as you start to open up the throttle, that's when you should start to build boost. At wide open throttle, you should have your, wide open throttle, maybe third gear, 4,000 RPM. I should be making maximum boost pressure, and that should line up with what other specification that the manufacturer says. So again, this vacuum pressure gauge, that's something that everybody should have in their toolbox, because you can do a lot of diagnostics with that thing. All right. So like I said, noisy operation, a lot of times these things get cooked out, they get abused. In a lot of cases, I feel like superchargers, are a little bit more reliable than turbochargers. They're spinning at less RPM. They're not subject to all the exhaust heat. We already talked about this, excessive oil, blue smoke, right? You're looking for blown out turbo seals, that type of thing. One other thing, I guess, related to this, plugged crankcase breathers. Turbochargers, because they're pressurizing the intake manifold, you have to have a really good positive crankcase ventilation system. If that system's all clogged up, you'll end up with back pressure inside the crankcase and the oil smoking and stuff. So that's something else to look at. So a lot of visual inspection stuff on turbochargers. Again, if you're replacing a turbocharger that's failed, you really want to flush out all the lines and make sure that there's not like little filter screens inside there. Crank the engine without starting it. Make sure you prime that turbo with a steady supply of oil. All that type of stuff. When you do a turbo replacement, I've seen a lot of people, they don't follow these steps and they end up damaging the new turbo that they just put on. Okay, so here's where the rubbers meet in the road as we kind of wind things down here. Comparing a supercharger to a turbocharger, right? Supercharger, you're losing efficiency. They're mechanical and how they work. Turbochargers, you do have some efficiency loss due to the increased exhaust back pressure, but overall, a turbocharger makes the engine more efficient, where a supercharger doesn't necessarily. Belt driven versus exhaust driven, oil and coolant, high frequency whine is what you're going to get from a turbocharger. Both of these are used by OEMs, so you'll see them out there. Here's really what I wanted to get to, though. What about the performance? With a, I got basically getting a little bit of feedback. With the supercharger, better low-end torque, no turbo lag, right? Large improvement in breakaway. You got power out of the hole with the supercharger. Turbocharger, it's more efficient and it's more high RPM power, right? So that's really one of the big things. It's like, where do you want your power in the spectrum? And are you putting the turbo on not only to add some power, but to make the engine more efficient, or are you just looking to make it accelerate quicker, right? So each one definitely has advantages, disadvantages there. Okay. Volumetric efficiency, we've talked about that a whole bunch, right? Here we have example where the compressor has its own efficiency ratings as well. And we looked at that on the turbo graphs and stuff, or the turbo maps. If you had a blower with a displacement of 10 liters, but it's only producing 7.2 liters, it'd be 72% volumetric efficiency. This efficiency rating right here talks about how much energy is put into the compressing the air without heating the air. Remember how we talked about how the screw style or Whipple style superchargers were more efficient than the root style. Remember that cool air is more dense, and that's going to make more power, all right? If we heat the air charge too much, we're going to kill our power gain. So really, we would want high volumetric efficiency to optimize the displacement, and high thermal efficiency to minimize the increase in air temperature. All right, so if we look at these efficiency ratings, what we end up with is that turbochargers are on average more efficient than superchargers, right? So with the turbo, I can have as high as 85% efficiency, whereas if I look at like a Roots blower, well, that's down at like 50%. As I said, the Whipple style or centrifugal style, you know, that starts increasing its efficiency, but it's not as efficient as the turbo. But you don't have the plumbing restrictions and everything else. So it's all about what are you looking to do and how much complexity do you want to, how much complexity do you want to add to the engine? All right, so as you can see, we did not make it to nitrous oxide, but it's been well over 2 hours and we need to stop. I don't know about you, but I'm dying. You've probably tuned out at this point. So this is a good place to pause. Hopefully it's making some sense. You know, I want to ask you guys, turbocharger versus supercharger, right? You know, what would be an advantage of a supercharger? Where does the supercharger really shine? I'll type it up here. Versus the turbocharger. Make sure I got your. You should be able to I'll unmute you guys. If somebody give me something. Why would you want to go with the supercharger? Let's say because it looks awesome. That could be a reason, right? Poking out of the hood, it looks like the Mad Max style.
I was thinking there's going to be more room in your engine bay.
Yeah, so I'm going to say supercharger, it's going to have less plumbing. Got less plumbing, a little less complexity. The supercharger also...
I did have one question.
Yeah.
How would you put like a supercharger or a turbo on a rotary? Would it work the same way?
You don't typically see superchargers on rotary engines, but you do see a lot of turbocharged rotary engines. And I think a big deal for turbocharging a rotary is actually because the intake and exhaust are both on the same side, a turbo actually packages pretty damn nice on a rotary engine. And you don't want a lot of air flow at low speeds, kind of shocking the rotors and apex seals. So I'm trying to think if I've even seen a supercharged rotary engine. I don't even know if I have, but I've seen a lot of turbocharged rotary engines. In fact, Mazda from the factory with the Gen 2 and then Gen 3, they both had those with turbocharged options. In fact, the Gen
I wonder if that
turbo,
could be a project for the RX-7.
yeah, the Gen 3 turbo, that RX-7 was available. That RX-7 was available in a twin turbo, a stage turbo setup. So, all right. So
didn't you plan on engine swapping it first anyway?
Yeah, I was still gonna keep it naturally aspirated though, and I was doing that for cost and longevity, right? Like you can see that your complexity goes way up when you're turbocharging, right? So where you see guys turbocharge rotary engines is when they're making a drag car or maybe a drift car or something. Not necessarily where they're gonna be running it at wide open throttle for long periods of time, right? Because even if I do a drift session, I might be doing like a 45-second run or a minute run. I'm not doing like a 1 hour or longer endurance race. And you tend to make a lot of heat and put a lot of strain on things. So I was going to keep it naturally aspirated. But anyways,
how do
so superchargers,
less more expensive
less
cars
complicated.
deal with that? Because I know like Ferrari and stuff, they still run like, say like Le Mans or something, and they have a lot of turbocharged vehicles.
Yeah, so they just they have really good cooling systems on there, right? And they closely monitor their boost levels and their temperatures and have good engine management to handle all that. And, you know, at the end of the race, they're rebuilding those engines, right? So, and they also have much bigger pockets for money.
So it's just the fact that they have the money to basically ruin a vehicle just to win Le Mans.
Yeah, or they have the money to engineer a vehicle that's going to withstand those harsh conditions, right? So they can build it to last for the time that it needs to last, and their time that needs to last is a lot smaller than me. Like me, I want to get multiple race seasons out of my engine package, right? They want to get maybe a race or a few races at most. So it's all relative. So anyways, to wrap this up, supercharger, low RPM boost, better torque, more pull off the line. So that's why you'll see it use top fuel drag, right? They're supercharged. Turbo, it's, I'll put that over here. I'm gonna choose the color. Turbo's gonna be high power and high efficiency, right? So it makes the vehicle more efficient. And that's why you see it's becoming more and more popular from the production standpoint. So either way, there's definitely some compromise.
One idea. Right? I know you did plan on supercharging the Model A. I wonder if, since I brought up twin charging so much, if it'd be possible for that, since there's so much open space to work with.
Yeah, so the plan is with our hot rod, the blue one. So the Model A is my uncle's, and it had a big blower on there, right? And I got to get that blower put back on there. The problem with it was when my uncle built it, he cobbled that blower on there, but the motor wasn't really built to handle that blower. So as soon as we started running it, it blew up the damn motor. So my goal is to build a motor that's stout enough, forged pistons, good rods, good crank and everything to handle the boost pressures, right? On our ARC hot rod, I wanted to do the same thing, but I actually have a different supercharger for that thing. And I have a centrifugal supercharger for it, and I have a root style supercharger for it. So we could actually compare the two styles of superchargers once we get that blue Model T that actually belongs to the college running. And you're right, with that setup, you got lots of, that's the advantage of those T-bucket cars, right? You got lots of engine area there, so you can put some weird things together and it'll still.
I was just thinking, all right, that's something that would be cool for a project to do.
It definitely would be a project. Definitely would. All right. So we need to wrap this thing up. I need to take you back to our Canvas webpage real quick here. And let's just see where we're at. I got to get rid of these scribbles. All right, here we go. So here we are in Canvas, and I just wanted to finish today. What do we have to do? What do you guys need to be working on? Okay, what's your homework, so to speak? Okay, well, let's go to the assignments here and look. We got some different discussions to do, and then we got some quizzes. In fact, maybe an easier place to see it would be to go to the calendar, and it's the computer's thinking about it. It's being slow, but it's getting there. We go. Okay. All right, so here we are. It is May 8th. We just finished talking about power adders. I have opened up an extra credit thing, so you don't have to do it, but an extra credit thing where, remember I talked about using the turbo catalog to pick the right turbo for an engine. I opened that up, so I have an assignment for you on that. That's available. Next week we're going to talk about nitrous, and then we're also going to talk about breaking in an engine, and we're going to do some review. But as far as stuff to do, we have a couple of exams on here to work on, and then we have our discussions to work on as well. So, and basically all this stuff, you know, it doesn't close out until the end of the semester. Next week is our last class session. Next week's our last class session, but you guys will have a few more days to work on stuff. The semester ends for American River College, I want to say right at May 20th. So what you need to do is, if you go into our course, where is it, 325, probably the most important thing to do would be to do your quizzes. So what I need to do, actually, I want to turn this on to student mode real quick. So I'm going to go to course home, the way. Student view.
That's another thing I was going to bring up regarding grades. The profile picture is put at 0, even though there's a profile picture on my account.
I need to fix that stuff. So I'm still working on. So normally in the past I didn't use Canvas for grades, and so I'm having to import what I had from Teacher's Toolbox into Canvas, and I'm still working on it. I've been rather busy the last 2 weeks, as I've been getting donations from Sierra College's program that's closing to American River College. And so I've been so focused on that donation, I really haven't had a chance to do a lot of that stuff, but I'll be working on this.
Another question, for speed and skill next semester, is it still going to be graded off of the repair orders?
Yeah, essentially it's just graded off of all the repair orders.
Okay, I was wondering if it was going to be the same or
yeah, no, it'll be the same. You know, I've been looking into if there's a way to if there's a way to electronically submit the repair orders or not. I'm a little worried about, you know, like if the virus picks up, or like how do I compensate for that in that class, right? So but essentially skill and speed class, it's just all about working on stuff, right? So okay, if I'm in student mode, if I go to quizzes, you'll see that there's 2 quizzes. This one is really the one that sums up our class really well. It's 14 questions. You can go through there. There's some short answer. There's some multiple choice. It's all the stuff that we've been talking about. And we have now gone over all this stuff, and you have resources there to help you answer the questions. Where are these resources? If I go to modules and I scroll towards the bottom, There's everything here from the Garrett Turbo catalog to a video link of how to CC cylinder heads, the video link we looked at a few weeks ago on how to degree your camshaft. I have the complete EFI University book on here and all the formulas and stuff. So if you just want, like, you're like, oh, what was that formula to do whatever? Well, guess what? I got them. So there's all your resources there you can find under the class resources tab in the modules section of our website. And we even have stuff like the dyno manuals and then our presentations and stuff like that. So you want to do that 14 question quiz. This EFI tuning exam is actually from EFI University. I'm going to be honest with you, it's considerably harder. This is more of it's more of like a do it to get the credit of doing it, right? Like I have the points graded to be less, and there's less priority on this. So you can use the EFI University book, and it'll let you know, like, if you were going to go through that program, this is what they expected you to know. And they tried to teach you all this stuff in 4 days, and then on the 5th day you took this test. So we have gone over a lot of this stuff, but because we spread it out over a semester, you know, it's a little bit different format. So try your best on this. I'm not going to grade it really strictly. I just want you to do it to see what it's all about. And again, it's all open book, so you can use your book to kind of figure these things out. It will definitely be a good review. There are some things that we didn't really get into just because of the scope of our class. Like this one, you're doing some electrical calculations. This one's going into different types of waveforms and stuff. What was very interesting is at EFI University, heck, they didn't go through this stuff either. They just gave you a test on it. So, so work on those 2 tests. There's a couple discussions on there for you to do. If you want to pick a turbocharger and get some extra credit points, you can do that. The turbo catalog is online, so you got lots of resources before before this website closes out. And I think the website will stay up until like the end of May. You know, everything here under the modules tab, that's all these resources. I recommend you guys go on here and download these catalogs and save these web links and stuff. Because if you're into building engines and tuning engines, you're going to want this information. It's got all kinds of stuff, and some stuff that might be right up some of your alleys. Like here's a link to an electronic fuel injection system for a small engine, and they have different ones that you can get from Honda clones to pit bikes to all kinds of stuff. So anyways, with that, I think that's a good spot for us to wrap things up for this week, because we're way over time. I appreciate you guys sticking with me. You guys, I want you all to stay safe out there and healthy, and spend some time learning about engines. And one other thing is Engine Masters, that show, it just popped up. The first season or so is available on Amazon Prime. So that's a fun one to watch while you're working on stuff. So stay safe, stay healthy. Next week, we're going to go into nitrous oxide systems, and I'm going to teach you the right way to break in a fresh engine build. Okay? With that, you guys take care, okay?
Thank you, Professor. Have a good
question.
Have a good week and stay safe.
I will. You too. All right, guys. Take care.